When you look at Jupiter, you are seeing the undisputed heavyweight champion of our solar system. We all recognize those beautiful, swirling, striped storms and that famous Great Red Spot. We are taught to call it a gas giant, but that label can be surprisingly misleading. If you tried to land a spaceship there, you would never hit a solid surface, but you also wouldn't simply float downward through a quiet, empty cloud of gas. Imagine diving straight into those colorful bands. The further you drop, the darker, thicker, and more violent the atmosphere becomes. To really understand how this massive planet works, we have to stop thinking of it as a fluffy cloud in space. Instead, we need to treat it like the ultimate deep-sea dive. As you sink hundreds of miles below the visible clouds, the sheer weight of the atmosphere crushing down from above causes the temperature and the pressure to skyrocket. Eventually, the hydrogen gas is squeezed so intensely that the normal rules of physics begin to break down. The lines between a gas and a liquid blur entirely. The hydrogen transforms into a supercritical fluid, a dense state of matter that behaves like a thick gas and a heavy liquid at the same time. You wouldn't hit a splashing wave to tell you that you've reached an ocean. The air simply becomes thicker and thicker until you are swimming through it. This supercritical fluid makes up the vast majority of the planet's volume. Jupiter is effectively a massive, swirling fluid ocean. And as we continue to drop further into the depths, that crushing pressure does something even stranger. About 7,000 kilometers down, the environment becomes hostile to basic chemistry. Down here, the pressure is millions of times greater than what we feel on the surface of the Earth. The hydrogen atoms are packed so tightly together that their outer electrons are stripped away, creating a freely moving sea of electricity. At this depth, the hydrogen actually starts acting like a metal. This state is what scientists call liquid metallic hydrogen. Because Jupiter is spinning incredibly fast, completing a full rotation in just 10 hours, it churns this deep ocean of liquid metal, generating massive planet-wide electric currents. This churning motion acts like an immense electrical generator, or a dynamo. It produces a magnetic field 20,000 times stronger than Earth's, stretching millions of miles out into space. This deep metallic engine room produces a massive magnetic shield and generates enough internal heat to ensure the planet radiates more energy into space than it receives from the sun. We know this engine room exists, but sending a physical probe down there to look at it is impossible. The pressure and heat would vaporize any metal we build here on Earth in seconds. To get around this, NASA's Juno spacecraft observes how the deep interior affects the space around the planet. By precisely measuring Jupiter's massive magnetic and gravitational fields from orbit, Juno effectively gives the planet a giant medical MRI. Before Juno arrived, researchers assumed they would find a dense, highly compact sphere of solid rock and ice at the very center. But the data showed something else. Juno discovered a fuzzy, dissolved core. Instead of a hard boundary, the heavy elements of rock and ice are smoothly mixed together with the surrounding hydrogen. Finding this mixed-up gradient interior changed the timeline for how we thought gas giants were put together in the first place. To figure out how you get a fuzzy core, we have to rewind the clock 4.5 billion years. Back then, our solar system was just a chaotic, swirling disk of gas and dust orbiting a young sun. One theory for how this happened is disk instability. This is the fast scenario, where a massive cloud of gas collapses under its own gravity to form a planet in just a few thousand years. The competing theory is core accretion. This is a slower process, where tiny pieces of dust and ice bump into each other, clumping into rocks over millions of years to build a solid core. Once that core is heavy enough, its gravity pulls in the surrounding gas. But young stars eventually blow the surrounding gas disk away. If Jupiter had taken millions of years to build its core, the gas would have disappeared before it could catch any. We'd be left with a much smaller planet that would look a lot more like Neptune. Since Jupiter did capture that gas, it needed a way to grow its core much faster to beat the clock. This is where pebble accretion comes in. Within the ancient gas disk, millions of centimeter-sized icy and rocky pebbles felt the drag of the surrounding gas. This resistance slowed them down, causing them to fall out of their normal orbits and go spiraling rapidly into the gravity of the growing planetary embryo. This chart shows the timeline of Jupiter's growth based on meteorite data. Notice the sharp, nearly vertical upward curve on the right, labeled runaway gas accretion. That continuous bombardment of pebbles acted like a turbo boost, allowing the infant core to reach critical mass, triggering a sudden spike in capturing gas. This violent feeding frenzy, or possibly a massive head-on collision with another early planet, explains why Jupiter's center is so strange. The core didn't have time to settle into a solid rock. It got churned up and dissolved into the hydrogen around it. Jupiter's massive size and its dissolved heart are the direct results of winning a violent cosmic race against time. Coming back to the present day, we can see that Jupiter is a dense, metallic world. Scientists are still investigating whether a giant head-on collision is the true reason behind that fuzzy core, and they are still mapping exactly how its internal dynamo compares to the magnetic engine inside our own sun. Jupiter is a massive archive of the early solar system, still holding the extreme heat and crushing pressure of its first billion years.